Welcome to Lecture 8, the second lecture video on electricity for Physics 4B. We continue to work with Coulomb's law and further develop the electric field concept in this lecture for this first week in static electricity. We start by looking at addition of electric force due to multiple charges, which actually looks a lot like how we have been adding any other forces in Physics 4A. But as some of the electric charge distributions get complicated, it's good to remind ourselves that superposition principle applies. And we can break up the complicated charge distributions, work out the influence of smaller pieces, and add them back up. And that's the example we work out in the second version of the electric force between a finite rod and a point charge. This time with the rod rotated 90 degrees, so that the line connecting the point charge to the middle of the rod is perpendicular to the rod. After we work out this expression for the electric force, we will use it to motivate the introduction of electric field as a way to package all the hard work that goes into evaluating these integrals. And we will take the limit of the expression as the rod length L goes to infinity to find one of the commonly used electric field formula. We will derive the remaining common formulas next week. Finally, we end this lecture set with a look at electric field lines, a graphical tool introduced to help us build our intuition for static electricity, which will be very important as we introduce and apply Gauss's law next week. Next week, we will still use Coulomb's law for a bit, especially for one or two difficult geometries, and we will demonstrate a better way to calculate electric fields which utilizes symmetries of the given setup. So I want to look at a couple more examples of calculating the force due to force due to charges. I want us to consider a couple more interesting scenarios. So the first one is net electric force due to multiple charges. Several charges. Let me actually make this easy for myself, and I'll say instead of several, let's say I'm just looking at due to two charges. And we'll just assume that we know how to extend it out to 3, 4 more charges. Some of your homework problems ask you to, so you'll get practice there. I'm just going to keep this easy for myself, and I will keep my charges along a line, which I always can if I have only two charges. So let's say I have one charge here, positive Q, and let me say I have another charge here. I think I want to make it negative, minus, but I don't want to make it the same magnitude because that sounds boring. So let me make it minus. People prefer 2 or 3? 2? Okay. Minus 2Q. All right, so I have these two charges. And what I want to imagine is I want to placing on a third charge of, let's say, third charge plus a small q, either somewhere along this portion here, or place it somewhere here, or place it somewhere here. And so let's say I placed this plus q where I drew it, here. What would be the direction of net force on this charge? So I'm hearing to the left. Does everybody say to the left? So how did you get left?
Because it should be pushed away from positive Q and towards Q.
Okay. You think it should be pushed away from positive Q and pulled towards negative, and they happen to be in the same direction. So, all right. Okay, so this situation was maybe a little bit too easy. What if instead this charge is over here? Now, what direction should the net force be?
Well, let's say positive Q. So I'm hearing to the right for some of you. Anyone else? So Chris, why did you say to the right?
Because the magnitude is really big with 2q, and then also the distance is really big for the repulsion. So if it's a large distance, it should be a weak force.
Okay, so you are considering these two forces, right? And let me formalize some of the things that you're already doing in your head. So to analyze this properly, what I really want is a free body diagram, right? So, I mean, some of you are already doing this in your head. That's the consideration you are going through. But let's just formalize it. Free body diagram of this charge Q. So what are the forces on charge Q? So now we actually change our mindset. In physics 4a, there was always gravity, right? Now there may not be any gravity because I only say charge Q. It could be massless. Or more likely, usually the situation is where gravitational force is so small, we can ignore it. So yeah, you can no longer say there's always gravity. Okay, what are the forces on charge Q? What's the exerting force on this charge? Yeah, I have minus 2q, and I have plus q. That could be exerting force on this charge, right? So yeah, so you have to switch over from your mindset in 4a, where there's always gravity and everything is contact force. That's no longer the case. So we have electrical force, which operates over a distance. And I guess what changes actually over from physics 4a is that in 4a, we relied a lot on your intuition. There were a lot of things that weren't specified in the system, and we just brought in out from your intuition, like gravity. Like even when we didn't say the thing was on Earth, we kind of assumed it was. With the physics 4b, you have to imagine that we are trying to describe fundamental physics. As in, if we have disarrangement made with anything anywhere, on Earth, on Jupiter, wherever, the description we are making still works. So here, what will help you guide your thinking process is that if you are talking about force on this plus q, that has to come from something that's described within the system. Like there's nothing external, there's no air resistance that you are going to worry about, there's no friction that you are going to worry about. So I have these two objects that's going to be exerting force. So I'm just gonna first work out their directions. Minus 2q, what direction is the force due to minus 2q? To the right, right? It's the attractive force towards it. So let me call it F minus 2. What about force due to plus q? To the left, because it's the repulsive force. And when you draw a free body diagram like this, to find the net force, you are just going to, how do you find the net force? It's not a trick question, it's an easy answer. How do you find the net force? Just add these two, right? Or if you want to indicate the directions, F minus 2 minus F1. That's the net force, right? I'm taking time to point this out because eventually we are going to give a very grandiose name to this. You've heard this term before once in physics 4a. You've heard of this thing called the superposition principle. Does that ring a bell? Yes? And the fact that you can just add these forces together without worrying about any interaction or whatever is a result of this thing called the superposition principle. It seems weird I'm giving this long, big name to something that you've been doing all along in physics 4a. But this becomes important as we start introducing more physical quantities. So today what we'll be introducing is something called the electric field. Electric field obeys the superposition principle. And much later, we are going to talk about energy, electrical energy. Energy does not obey superposition principle. So knowing whether a quantity follows this principle or not is something important for you to know. So, with the forces, you would simply add them because they follow superposition principle. And so here you would just add it. To actually finish calculating it, I would have to specify some additional parameters that I haven't yet. I'd have to tell you that the distance between them is maybe d, and the distance from the charge to the minus 2q is some distance x. Once you have all of that, then it's a simple exercise copying it down from Coulomb's law. So you'd write down net force is equal to k. Let me factor out k so that I don't have to keep writing it down. K times, so charge q1, so minus 2q times plus q, so q, divided by the distance squared, x squared, minus f1, so plus q, times q, over the distance squared, so d plus x squared. D plus x squared. Let me ask you this question. Is this correct? There's one way to, if you're not sure if it's correct or not, let's finish through the calculation and we'll see if it agrees with our intuitive answer. Let's just finish through the calculation. So all of this equal to, let me factor out the minus sign. So minus k times, I guess I have to combine the fraction, x squared times d plus x squared, this times that, so I don't know. 2q times d plus x squared plus x squared times all of that. So q times x squared. All right. What does this result say that the direction of our force is? Seungmin, what does the result say that the direction of our force is? To the left. Does that sound right? No, right? We weren't expecting a leftward force. So I deliberately made a subtle mistake that I want you to catch. So that I'm going to actually change one of the conventions that I used to use in physics 4a. In physics 4b, as we start talking about more formal mathematics, more fundamental laws, I actually discard one of the conventions that I used to use in physics 4a. And I really want to bring your attention to that. That's why I'm deliberately making this mistake and having you catch it. Chris?
You just use the magnitude of the charges, not the positive or negative of it?
I put minus q here, minus 2q.
Yeah, I'm saying it should just be 2q.
Oh, I should have used just the magnitude. Yeah, because if you remember my convention in physics 4a, I tried to put in all my signs into the equation, and I let the quantity stand for magnitude. So if I'm trying to follow the convention here, which I can, then what I would have to remember is that it's not this. I really need to have absolute sign around this, and technically absolute sign around this. And this is what I'll tell you. As you're doing more formal mathematics, all that absolute signs, they get annoying. So you don't want to deal with that. So really what you should start doing at this point is discard the convention that I used to use in 4a. It's useful in 4a. It helps to build up your intuition. But what we are going to do in this class is help build up your formal mathematical skill. So I'm going to discard the convention of putting the signs into equations. Instead, I'm going to let signs be absorbed by these quantities. So I'm simply going to say net force is F2 as a vector plus F1 as a vector. All right? So if I'm doing that, so except this is with a plus sign, everything is fine. The thing I would have to be careful with is that these are vectors, and in Coulomb's law, there's this unit vector here. So with the minus 2q, the unit vector points this way. Let me call it, I don't know, L hat for leftward. For plus q, the unit vector happens to also point to the left. It's pointing towards this charge. So they are the same unit vectors. So they have both have the same unit vectors L hat. And if you wanted to, you could factor it out and have this unit vector here. So my final result would actually be, instead of these two adding together, they actually should subtract from each other, as you were expecting. So it's a question of, the quantity inside here. Do you want it to be positive or negative? Think carefully. What do you want the direction of the force to be? To the right, right? L hat is pointing to the left. So what sign should the component be for your eventual force to point to right? Negative. So we want this to be negative, meaning we want this negative quantity here to be bigger than this positive quantity here. So the question is it? Yeah, so what's the argument you can come up with, Chris?
When it's divided by, it's a lot bigger. The d plus x is
Yeah.
bigger than x.
So this second one, the denominator is bigger. And on top of that, here, the numerator is bigger. So on both counts, this quantity should be bigger in magnitude, so negative should win. Good? Does all of this make sense? Yeah, and this change in convention, I'm going to follow it more or less throughout this whole class. Because the math you will see in this class is more formal than what you saw in Physics 4a. So unless I'm doing a Physics 4a type problem, I will try to keep to this convention where the quantities themselves contain the direction, and the equation simply tells you whether you are adding or multiplying them. Good? All right, let's wrap up. Let's use this example to wrap up one last discussion. So let's say I want to find a place to position along this line to place this charge so that net force is 0. Where would I place it? In the middle, okay. Let's imagine we are placing it in the middle. Let's say it's somewhere here, Q. What's the direction of force from minus to Q? Yeah, to the left, right? Because it's negative, it's attractive. What's the direction of force from positive Q? They are both positive. So is it attractive or repulsive? It's repulsive. So if this is being repelled from this, the direction is no. Yeah. If it's moving to the right, is it getting repelled?
Oh, no.
Yeah, to the yeah.
Think of the other cube.
Yeah. So when you're starting out, it helps to think: is it attractive, repulsive, and attractive or repulsive from what? That's what this is actually helping remind you. Okay? So when it's in the middle, both of these charges produce a leftward force, meaning they will not balance each other out. So nowhere in the middle will actually work. All right, give me another suggestion. So this was region 1 that we tried. Let's try a different region.
Far right. To the right of the big cube.
So it might be somewhere in this region. Now, will it be every point in this region? Probably not, right? It seems like a special point. So let's try to work out an expression to see what it should be. So let me move this charge and let's put it here. Let's say the charge is somewhere over here, plus Q. And let me move this label over so that we say, these two charges are still distance d apart. And charge plus Q is distance x apart from plus Q. So if we want, we can go through all this again. So this is the new free body diagram for this charge. So what's the direction of force from minus to Q? Yeah, it's attractive, and attractive means to the left this time. So this is the force from minus to Q. What's the direction of force from plus Q? Repulsive, so that means to the right. So to the right, F1. They're, like in this other region, they are opposing each other. But unlike in this case, what I'm hoping for is that there's a place where we can find the net force will add up to 0. So let me write down Newton's second law. Net force as a vector is equal to F minus 2 as a vector plus F1 as a vector. The unit vectors that are in effect now are not the L hats. So I'm looking for the vector that's pointing from the source to the target. So it's this unit vector. Let me call it R hat. R for right word, not for the usual reasons. So call this R hat. They both happen to be the same unit vector. So when I add these two together, what that would be is, so I'm applying Coulomb's law now. So K times the charge minus 2Q times the small charge plus Q divided by the distance, D plus X squared times the unit vector, R hat, plus the second vector, K times positive Q times Q divided by the distance, X squared times R hat. Let me factor out all the constant things that will factor out so that I don't have to keep rewriting them. It's annoying having to write them all. There's K in both of them. There's BQ in both of them. Small lowercase q in both of them. There's R hat in both of them. Okay? So let me write down a version of expression with all those factored out. K, Q, Q, R hat. That's all the common vectors. So what we are only interested in is times minus 2 over D plus X squared plus 1 over X squared. Okay? So this is what the question comes down to. What is the position X that will make the net force equal to 0? So how do you proceed from here? Yeah, say that this is equal to 0, and then solve for X. And I guess so none of these quantities actually matter. So let's just do that. It shouldn't take too long. So say that, so minus 2 over D plus X squared plus 1 over X squared is equal to 0. I'm essentially saying, these quantities probably are not 0. So I'm going to let this equal to 0. So that's what this is. Feel like the easiest way to simplify this is multiply through by this and this. Then you end up with minus, so this cancels out, so I get minus 2x squared plus, and when I multiply through by this and this, x squared cancels out, and I get this. Right? So plus d plus x squared is equal to 0. Expand this out, you get d squared plus 2dx plus x squared minus x, so these two cancel out, or partially cancel out, to give you minus x squared plus 2dx plus d squared is equal to 0. Does this simplify more? So if I multiply through by minus 1, I get this. It doesn't simplify, right? No. Yeah. So this is where you have to use quadratic formula. Oh well. So x is going to be equal to square. Let me slow down and label things properly. So the 1 that's implied here is my a, minus 2d, that's my b, and this whole minus d squared is my c. Quadratic formula is minus b plus minus square root of b squared. All right, let me write that down. Minus b, so it'll be plus 2d plus minus square root of b squared, so this thing squared, 4d squared minus 2 b squared minus 4ac, right? Minus, why am I forgetting this? So minus 4 times, okay, so 1 times minus 1, so it's going to be plus, sorry, it's d. So plus 4d squared, right? Why do I, sorry, I'm having a senior moment. Divide by 2a. So divide by 2. All right, so I get x is equal to d plus or minus, it's applying 2 here. So plus minus square root of, so 2 inside here will cancel out 4, so I get 2d squared. So I get x is equal to 1 plus or minus square root of 2 times d. Yeah?
Should a be negative 1 because of minus 2x squared plus x squared?
Yeah, sorry, I skipped some of the steps. Let me write out the steps so that I'm not confusing everyone. Yeah, I was afraid as I was doing it that I might do that. So, with all this written out, minus 2x plus x squared, that does give you minus x squared plus 2dx plus d squared is equal to 0, right? And to get from here to here, what I've done is I've taken this and I multiplied it by minus 1. So the a is 1, but b and c are negative. Okay. Yeah, that's our answer. Do we really have 2 different answers? So, I have this plus minus. Which one is correct? Is it plus or minus? So, square root of 2 is about 1.4. So either this charge is at about, at about distance of 2.4 from this point here. Or if we got a negative answer, that would mean it's over here. But we already ruled that out, right? So what does that negative answer mean? I'll just answer my own question. That negative answer means that when this charge is here, you actually have to change some of your equations. Because when this charge is here, all of this is fine, but this will actually need to change. Because the unit vector now points to the left, not to the right. Yeah. So this expression that we are deriving here, it's only valid in this region. So only the positive answer is valid. So the actual answer for x here, x that makes all of this happen, that x is equal to 1 plus square root of 2 times d. Right? Everyone okay with this calculation? So, this is it's not a complicated calculation, right? Yeah. This is a simple toy example, but I want you to use this to start getting you used to some of the ideas that the electric force described by Coulomb's law, it's a vector quantity. And because it's a vector quantity, in the law, there will be a unit vector that tells you what the direction is. And that direction, it's an intuitive direction. It's sometimes it's called the radial direction. That's what this R is really meaning. Radial meaning it's going from the source to where the other charge is. But there will be situations, in fact, this is our next example, where this direction is somewhat complicated and you have to draw it and work it out carefully. So that's what I want you to introduce with this reasonably simple example. Yeah. Let me ask you this one last question before we move on. Would any of this change if this was a charge of minus q instead of plus q? As in, would this still be the same answer? Chris, why wouldn't it change?
I just kind of feel like a brain. Now it's being attracted to positive Q and repelled by
Minus Q, yeah.
So maybe it would be the same.
How would you prove it if you had to prove it? Other than going through the whole calculation all over again. Here's a neat trick, and this is why we start introducing mathematical formalism, why we start being more formal with the mathematics and follow these careful new conventions. Because when you've done things that way, you can actually do this wholesale replacement. All I've done here is I've taken plus Q and I change it into minus Q. So what that means is every time I see a Q, I should, to get the result that I would get, I should take wherever I see Q, replace with the minus Q. Replace it with the minus Q. And if I had nothing better to do, I would do it for every single line. But really, all I care about is the line at the very end. The minus Q here, and the fact that there's no Q anywhere here. And in fact, you can see it in this line. Minus Q here, well, I don't care. It's this thing I want you to make a negative. So the calculation from here on is not affected by the sign of the charge here. So I want to just point this out as something interesting. We'll come back to that as we talk about electric fields. Yeah? At the end of the day, the algebra is pretty simple. It's not a difficult math. It's just a new way of doing things that's departing from how we've been doing things. Let me give you something that's more challenging than that. It's the other version of the calculation we did on Monday. Do you guys remember on Monday where we calculated a force between a uniformly charged rod and a point charge? Do you remember that? Yeah? We did on Monday. Oh, I think it was arranged this way. We did this on Monday. Today, we are going to flip it around a little bit. Well, we're going to flip the rod 90 degrees. So I want to figure out the force between a rod oriented this way and the charge here. Let's make it easy for myself. I will just put the charge at the along the line, going through the midpoint of the rod. Good? So let me draw the picture here so I have something to refer to without having things in my hand. So let me call this force between uniformly charged rod and a point charge. So this is the geometry. I have a rod of length L. And let me make this easy for myself this time. Instead of giving the total charge of the rod, I'll just say it has linear charge density lambda. And hopefully you remember. By the way, lambda is a pretty standard symbol for linear charge density. So get used to it. It's defined as the total amount of charge divided by the length of the object. And it's a pretty standard symbol, so I'm not the only one using it. So I have a uniformly charged rod of length L. I'm not labeling the length right. Of length L. And I have a charge placed in this way. I have a line that's going through the middle of the rod so that it's symmetric, it makes things easier for me. And at some distance, let's call it distance d from the rod, I have a point charge plus q. So the question we are asking is the same question we asked last time. What is the force on this charge plus q? Let me have you think about it while I erase the rest of the board. Do you have some intuitive sense what the direction of the force will be? Let's say lambda is positive, just to make things simple. Lambda is positive. What should be the direction of the force? To the right? Like directly to the right or not tilted up or down? Directly to the right. So why do you think there should be no vertical component of force? uniform, and one more thing. Let me ask you this way. What if I place the charge instead over here? Let's say call this plus Q2. What do you think the direction of the force on Q2 should be? Still directly to the right?
Yeah.
Think carefully. Downward or upward?
I guess slightly up.
Yeah, so looking at this Q2, this is the way you would analyze it. So you know, it's the same procedure we went through last time. It's hard to think about the whole rod, so you are going to think about the small sections of the rod. So from this small section here, the direction of force is directly rightward. Great. But from this small section here, the direction of force is slightly upward. And as you go to these other sections, which are farther away, so less force, but they all point slightly upward. Instead, so none of them point downward. All of them, if anything, point slightly upward. So when you add all these forces together, the net force might go this way. Good? So, you know, the calculations we do tend to be pretty formal, as I keep saying. I'm probably going to say the word formal like 5 more times today. So it becomes especially important that you spend the effort to develop your intuition. What that means is that before you do the calculation, you try to develop an intuitive picture of what it should look like. And then after you finish the calculation, and you see if your calculation agrees. If it does, great. If it doesn't agree, one of two things happened. Either your intuition was wrong, or you made a mistake in your calculation. I'll tell you that for electrostatics, most of you actually have good intuition. So most of you, so if you get something that's different from your intuition, usually it's the fact that you made a mistake in the calculation. So let's go through the calculation here. So we went through this last time, that we cannot use Coulomb's law directly because we run into this problem of what distance? Because when you are looking at between a point and a segment, the distance can vary as much as this distance here, which is d, and as long as this distance here. How long is this distance? Well, it's based on half of L. So it should be square root of d squared plus L squared over 4. Everyone good with that? Yeah. Better get used to trigonometry and geometry. It's going to come up. Okay, so there's a range of distances. So yeah, it's going to be a little bit tricky. So let me actually put it this way. We reintroduce the force as a vector so that we can deal with it as a vector. So let me draw a representative contribution to the force from one of these segments. By the way, I'm pretty sure the way I'm doing this is slightly different than your textbook. So look at both approaches. I like the one I do better. That's why I do it. But so there's something you can do called pairwise cancellation that would help you sort out some of the answers. But I'm going to actually do the more formal way of calculating things because there's a power in the formal approach, as long as you make sure to develop your intuition alongside. So let me just pick a representative piece here. I'm going to use this piece as like an arbitrary piece along the rod. So I'm going to need a parameter to parameterize it, some position y. This is a piece at a position y. And it's a piece of the size dy. That will come handy later when I need to know how much charge is in it. It will be the charge density times the dy. Okay? Now, what I need to figure out is the full vector quantity of the force. So what is the direction of the force due to this small segment of the rod? Sort of slightly downward, right? So it's not in any one particular, it's not directly to the right. It's some general representative direction. So this force is what I'm going to call force dF. Small contribution to the force due to this small section of the wire. Yep. And everyone here knows the expression for this small contribution? Where do I get the expression from? Yeah, now I use Coulomb's law. Now that I'm talking about small section, I can treat this 2-point charges interacting like Coulomb's law describes. So this is going to be K times, let me just write out the amount of charge. Save me some steps. So lambda times dy. That's what the amount of charge is going to be, right? Okay. Times the amount of charge here, plus q, or q, divided by the distance squared. Someone tell me the expression for the distance. What is the expression for the distance? Crystal? Okay, square root of y squared plus d squared. Yeah, you are looking at, so what Crystal is looking at is this right triangle, right? And the distance is the hypotenuse. All right, so I'll write that. That's the distance. Square root of y squared plus d squared. But you know what? I'm going to be squaring it, right? So let me just get rid of the square root and say, well, that's what I'm dividing by. I'm not done. I need the direction of the vector. I need what I'm going to call, well, I mean, what we will call, we need a direction r hat. So this whole force is going to be all of this quantity times r hat. So you know, just to sort of symbolically, that's all it is. You take this expression here. Oh, I really didn't plan my spaces. Well, you take this expression, df, and if you integrate it along the rod, then you should be able to get the whole force. Because, so you know, imagine getting contribution from small sections of the rod. This small section moves from one end of the rod to the other end of the rod to get all the contributions that will give you the force. Now, if you are doing the calculation this way, you say, you know, this is equal to, you know, all of this integrate. So if you are integrating along the rod, then you are varying the parameter y. You would say y goes from minus L over 2 to L over 2, k lambda times dy, q over y squared plus d squared, r hat. So everything here seems to be already in terms of y. So you write it out. Factor out all the constant quantities, k lambda q r hat times, well, integral from minus L over 2 to L over 2, dy over y squared plus d squared. And you do all of this, you get an answer, and you look up the solution in the textbook, and you'll find that your answer is wrong. What went wrong? There's a very subtle mistake made once more. So the reason I'm pointing it out this way is that when I was a graduate student, I found that every time I tried to do this calculation after a few years, I would always make this mistake. So I wanted you to develop an ability to spot this mistake from early on, so that when you forget all of this and try to do it again, you'll be able to spot your mistake again. So there's a very subtle mistake made in this series of steps. There's something I've done that I actually couldn't do and shouldn't have done. Dy is fine. So dy was here, dy is here, I kept it here. Dy is the reminder that y is my integration variable. And also it actually has physical meaning, that's the infinitesimal length. Let me give you a hint. There's a symbol that I took outside the integral that I should not have. It actually could not be taken out of the integral. Lambda is okay, uniform density. Wait, what were you saying? R hat, yeah. So what's wrong with taking the r hat outside the integral? It is relative direction, so what does that mean? So, if imagine this, visualize this. As I take this, let's say I move it downward a little bit. What happens to our head? Yeah, it changes direction. What that means is this our head, it's a function of y. Yeah, this is the kind of thing you will begin to see when you take multivariable calculus. You will get unit vectors that are not constant. Unlike x hat, y hat, and z hat, which are constant. This is an example of a unit vector that's not a constant. It's a function of parameter. So that means, yeah, I should not have taken it outside the integral, because when I take it out of integral, what I'm saying is that, well, that's a constant, I can take it out. Well, it's not a constant, I can't take it out. So that's the mistake made. And so what I need to do is I have to do a more careful job of expressing this r hat, express it in terms of the constant unit vectors. So what I really need to do is I need to go through this step. Say that r hat is equal to something times x hat plus something times y hat. Oh, darn. That means I need to define my axis. Let me define it the normal way, x and y. I mean, let's not be creative here. So that's my axis, and I have to express r hat in terms of these two constant unit vectors. The parameters that go here are going to be how it's a function of y. So, it's an exercise that you need to go through. I'm just going to stare at this for a while. So, I'm looking at this here. Let me draw it a little bit bigger so I can think a little bit better. So I'm trying to think, all right, so I want to express this as something like this vector here, and this will be my x and y component, right? And these are really x and y component, right? So if I knew this angle somehow, then I could express this. Yeah, wait, I know this angle here. This angle here is this angle here, right? So I could say it's cosine of theta and sine theta, but that wouldn't quite work for our purposes because I really want it as a function of y, not theta. So that's why I have to go through this step. This theta can be expressed as a function of y. So looking at this triangle here, let me draw the triangle also. It looks like this. Theta, y, d. So what I have is cosine of theta. By staring at this triangle, I can rewrite it in terms of y, constant d, and this hypotenuse, which will be square root of y squared plus d squared. Good? So what's cosine of theta? D, not just the d, but d over something. This is your right triangle. What is cosine? Yeah. D divided by the hypotenuse. D over square root of y squared plus d squared. What about the y component? Or sine of theta? Yeah, y over square root of y squared plus d squared. Good? Any questions? All this seems okay? By the way, this technique is a technique called drawing the triangle. It's used to essentially rewrite expressions in terms of trigonometric function of an angle in terms of the other parameters that you are given. How many people have seen this technique before? I feel like the first time I learned this was like somewhere in trigonometry. If you haven't seen this before, this is a pretty common thing that comes up from time to time in physics, where you have something that's potentially complicated function of theta. Well, you draw the triangles and you realize the trigonometric relationships. Then you can write down something that's simpler than what you would do if you are going through arc sine, arc cosine. Good? All right, so I have that. So I had to plug this in for here. Do I want to write it in? Yeah, I guess I kind of have to. All right. So this time, let me factor out the things that are actually constant, and I will write out the rest. So it'll be factor out the things that are actually constant. That's k, that's literally constant, times lambda. It's constant because it's uniform density, times q, because it's only a point charge. And I think that's it. So the rest is integral of, now it's going to have two terms. It's going to have the term containing x hat and the term containing y hat. So let's just write it out. It's, can I? No, I can't factor out this. All right. So d times dy over, so this can actually combine with this to make a slightly simpler expression, y squared plus d squared power of 3/2 times x hat. Everyone good? Okay. Let me write down the second thing. Let me write it this way to make it clear it's factored out. Plus integral of this thing, y times dy over y squared plus d squared raised to the power of 3/2 times y hat. Let me fill in all the details that I've been skipping. So I like to be a little bit fastidious about this sort of thing. Y goes from minus L over 2 to plus L over 2. Y goes from minus L over 2 plus L over 2. And close the parenthesis. Good. When you see all of that, I hope some of you realize that something simplifies right away. Something just cancels out, goes to 0. Anybody see what goes to 0? You have two integrals. One of them is 0. Which one? Do you guys remember the whole even, odd integrand when you are integrating over an even interval? Yes? Okay, so here, this is an even integrand. Fine. This, are you guys convinced that this is an odd integrand? Y over all of this. Odd? Right? Because the denominator is even. So numerator are odd, so they must be odd overall. What do you get if you integrate an odd function over an even interval, as in you're going over a symmetric interval, from a minus something to positive the same quantity? 0. Area under the curve cancels out area over the curve. Right? Yeah?
How did you know that the y is odd? The d is
So this is the bit from calculus. So imagine sketching y. So in the xy plane. So not x, yeah, I guess. No, y, function of y plane. So this function of y is just a line, right? This is f of y is equal to y. We call this odd. When we say something is odd, formally this is what we mean. F of minus y is equal to minus of f of y. When we call something even, this is what we mean. F of minus y is equal to, well, it's just equal to f of y. This is the words describing symmetry of a function. Does this ring bells for everyone? Yes? You guys covered this in calculus? Calculus 1, hopefully? Yeah, so geometrically what this means is that you flip it over the axis, and then you kind of have to flip it over the horizontal axis again to get the same thing back, or something like that. Or if the even one, it has mirror symmetry. If you flip it over, it looks the same. So an example of even function would be f of y is equal to y squared. So this is an odd function. So this is an odd function over symmetric interval. So it's 0. We don't have to do anything. You can actually do the integral. It turns out this is the doable integral. You can do the u substitution here and actually do the integral. And when you do it, you'll find out that it's 0. So I wanted to save just some of that work. Anybody here know how to do this integral? Any suggestions? Try it in your head. If you try to substitute u equals y squared plus d squared, what do you get? Does it work? You have to use trig substitution. So u substitution will not work. You have to do trig substitution. And I'll just fast up and say this. I will never give you an integral problem where you have to use trig substitution in this class. So instead, for these few problems where I kind of have to in lecture, I'm just going to use Wolfram alpha. It's easier. So I'm going to integrate. So what I want is integral of 1 over x squared plus d squared, kinda. Maybe I should say this. Y squared plus d squared. Let me actually do the full length and d. And actually there's more. There's 3 halves here. So let me put in the 3 halves. 3 halves with respect to y. Wolfram alpha has a level of natural language processing. So when it processes it and tells you this is how it understood you, make sure it understood you correctly, then all right, that's my answer. Doesn't look all that difficult. But it requires a trig substitution, which is why I'm not actually doing it. I'm just looking it up. By the way, in a calculus class, you actually would have, unless you are in the trig substitution chapter of the book, you would have looked it up in an integral table. That's what I'm essentially doing here, except easier. So all this integral comes down to this. It's equal to, these constants are still there, KLQ. I have the antiderivative of the x hat times the antiderivative of this, which is y over d times the square root of d squared plus y squared, evaluated from y equals minus L over 2 to y equals L over 2. So, we got something that we were intuitively guessing before. What were you guys saying about the direction of the force here? They should be to the right, right? Well, what's the implication of this whole thing being 0? Yeah, they don't have any y component. So, this should, when you see this, that should be encouraging. That the y component canceled out, that the only thing remaining is the x component. So now, if you want the actual answer of what the force is, then you would evaluate it. Let me just copy it down here. So when you plug in this, I guess it's L over 2 here, minus L over 2. The denominator is the same either way. So it's going to be 2 times one of these plugged in. So when you calculate the force, so the force pointing this way, this force is equal to K lambda Q times L, from L over 2 times 2, L, divided by, well, let me erase this, divided by all of that. D times the square root of D squared plus L over 2 plug it in. So L squared over 4. All pointing in the x direction. Yeah. So this is a long calculation, but I think this is doable if somebody told you, gave you this out of a table of integrals. So I'm actually going to piggyback off of this a little bit, which is why I haven't raised it entirely. So, you look at this expression, it looks super complicated, right? Yes, everyone agrees it looks complicated. So what I'd like to be able to do is come up with some limiting case where I can simplify this expression. So the physically what we are looking at is this, right? Interaction of a rod with a ball. So by limiting case, this is what I mean. I could make this ball very, very far away, or I can make it very, very, very close. So which limiting case do you want to look at? To try to make this expression simpler. Very, very far away? Yeah, if you do very, very far away, I won't write it down because it looks pretty simple. If you say D is much, much bigger, then you look at this expression, see what you can ignore. This is what you can ignore in that case. Right? So the denominator becomes D times the square root of D squared, or that's just D squared. So in that case, what you get is you get Coulomb's law back. Because what you have is K times the lambda times L, that's the amount of charge in the rod, times Q, amount of charge in the point charge, divided by distance squared. Which is what you would have expected, which is what you should get. Now, would this also simplify if you said that this charge is very, very, very close? Let's see what happens. I would actually like to draw it in a different way. Rather than saying that the charge is very, very, very close, I'll say charge remains here, but the rod becomes very long. That's an equivalent way of saying it, right? So I can consider the interaction between infinite rod and point charge. So the rod becomes infinitely long, but it's going to have the same charge density lambda. So if you get the entire rod, it'll be infinite amount of charge. So I won't go there. And for this infinitely long rod, I say there's a charge Q here at some finite distance d, and ask the question, what is the force? Well, I take this expression, and what limit am I taking? So I'm going to take one of the quantities, let it go to infinity. What am I letting go to infinity? Yeah, so I'm taking that. I'm taking the limit of L going to infinity of all of that expression. K lambda Q L over D square root of D squared plus L squared over 4. All right, I don't know what to do with that. Let me ignore it for now. I think I know what to do with this, so let me do that. What happens with this expression? Is there something you can ignore? What can you ignore? That's the infinite quantity. You can ignore the infinite quantity. That's the thing. Yeah, D becomes infinite, much, much smaller in comparison. So when it's being added to something infinite, you can ignore it. So you have square root of L squared over 4. So this whole quantity is actually equal to L over 2. Right? So, this L cancels with that L, which is good because I don't want anything going infinite in my final expression. So I actually end up with a finite amount of force. Let me write it here. I get force is equal to K lambda Q times, I've divided by 1/2, so there will be 2 K lambda Q divided by D. I get this very simple expression for the interaction between infinite rod and a point. Okay? And believe it or not, you will see this expression again. We are going to redo this sometime next week in a different way with a different context. The way we did it is the hard way. I will try not to do it this way again. So that's a pretty simple expression, which is encouraging. Let me tell you a discouraging idea. So all right, so you feel like you understand the interaction between an infinite rod and a point charge. Let's make it interesting and say you want to see the interaction between an infinite rod and another infinite rod. Now, you can look at the total force because that will be infinite, but let's say you're looking at force per unit length of this. How would you do that calculation? You might say another integral, right?
Would you just do 2-point?
So yeah, it really comes, the difficulty really comes down to this, and it comes down to some measure of tediousness. And it really comes down to the fact that the way Coulomb's law is stated, it's a law of interaction. It will always involve interaction between two bodies. It will always have to involve pairs of charge. And calculationally, when you try to calculate different things, this limitation is very limiting. So what we would like is a mathematical device that lets us separate away from that paired model. This is what we would like to be able to do. So let me go back to the simpler picture here. Let's say we are dealing, because I'm just saying conceptual ideas. Let's say I'm handling with a point charge here, point charge plus Q, right? And in the Coulomb's law model, if I have this point charge just here, nothing has happened. There's no force anywhere. This charge doesn't exert force on anything. Nothing has happened. The interesting things start to happen only when you introduce a second charge, plus Q sub 2. That's only when interesting things start to happen as these two things interact and repel each other, right? But, think to yourself, so when you look at this empty space, when you have completely empty space versus when you have placed a charge, has something changed? Like, in an intuitive sense, would you say that the empty space is functionally equivalent to, so empty space, would you say that the empty space is functionally equivalent to with the empty space with a single charge? Or that single charge does have an effect. It did change something. Yeah, here's one example of what it changed. The next time I place a charge, it's now going to feel a force. With empty space, that wasn't the case. So what we want is a mathematical device that tells us that even when you have a single charge, something has changed. Something about the property of the space around it has changed in such a way so that now when I place an additional charge, it's going to feel a force. So that's the thing we are going to call electric field. So conceptually, this is how, this is the distinction. So with the Coulomb's law model, this is how things work. If you had charge 1, then from charge 1, you directly went to applying force on charge 2. This is a model that you would call Coulomb's law model, where charge directly applies force on second charge. Unless you have those pairs of charge, nothing is happening. The new model that I want to move us to is the field model. And to tell you the truth, we are not changing anything physically. We are just introducing a mathematical device for mathematical convenience. At least to start. I'll change my tune at some point. So with the field model, what we say is that when you have charge 1, we don't look for another charge to immediately apply force to. What we do is that we say, all right, charge 1 is going to produce or generate. I don't think there's an actual standard word for it. Produce or generate a field that we are going to call electric field. What is this electric field? Who knows? What's important about this electric field is that once you place another charge within this electric field, once you place a charge 2, then this electric field is going to apply force. So we look at this field as a mediator. We don't say charge 1 is what's applying force directly on charge 2, we say all that charge 1 does is it produces the field, and this field will now apply force on charge 2. So this might seem a little bit contrived now, but as we go into more complicated examples, you will see the value of this field approach. And actually, just looking forward to the end of the semester, this electric field actually gets its own physical, I guess, manifestation. Anybody here know what an electromagnetic wave is, or have heard the word? Like, you've heard the word electromagnetic wave? What is it wave of? Does anyone know? Is it wave of charged particles, or what is it? Well, photon is the light particle, but we are not doing quantum mechanics in this class.
Isn't it just the movement from north to south?
So there's actually magnetic field there too. That's why it's called the electromagnetic wave. But what is waving? I mean, electromagnetic wave is a general term for light, but there's some quantity that's waving. That's why we call it wave. It's this field. It's the electric field that's waving. It's the magnetic field that will be waving. And this is what I like to say. So electromagnetic waves can kill you. Gamma rays, it's an electromagnetic wave. Something that can kill you is not just a mathematical device. It's something that has an actual physical existence. So let me just briefly describe. So that's the motivation for electric field. And the ideal field is actually pretty simple. So this is, let me just start by defining field. So here's the definition of electric field. Well, here's the defining equation for electric field. I'm going to do it slightly backward, or it'll look a little bit backward. Instead of saying what field is equal to, I'm going to say what force is equal to. I'm going to say that electric force is given by charge times electric field. So this is the defining equation for the electric field. Do you want to know what electric field is? Well, this is how it's defined. Somebody asked me why I'm not simply writing this more comprehensible way of electric field is a force divided by Q. Like, why am I not doing that? Why am I insisting on this weird way of writing things? Oh, no one's actually asking me that? Oh, I asked myself, I'll answer. It's sort of my opinion about what's fundamental. So if you write it this way, you are sort of saying the force is what's fundamental, and the field is derived from the force. I don't want to say that. Field is actually what's fundamental. That's the modern physics view. Field is fundamental, force is the effect of that field. So going back to this point charge, the moment we place a point charge here, what we are saying is that we have actually changed the space around it. We have changed the property of the space around it in such a way that if I place some charges around it, we call them test charge. So you have to imagine charges that are small enough that it's not going to affect anything else around it. Like this is so much bigger than that when I place another test charge here, that this won't really feel this charge. So imagine placing all these test charges around. Then from Coulomb's law, what happens to all these test charges, right? What happens to them? Let's say they're all positive. Then they all get repelled radially outward, right? So this charge gets repelled radially outward this way. This charge gets repelled radially outward that way. This charge gets repelled radially outward this way. This charge gets repelled radially outward that way. And to get a sense of how this charge modifies the space around it, you have to imagine placing these point charges everywhere and looking at their effects everywhere. And for this simple situation, it's actually not that hard to imagine. Like, what do you think will happen? Anywhere you place, they will get radially pushed outward, right? So we draw a representation of that. So these lines. So these are, let me just finish this line. So this line here, I have 6? I don't like 6. Let me draw at least 8. Lucky number. So these are what we call electric field lines. And we'll go more into this later. For now, this is the graphical representation of the fact. The physical fact that this point charge being placed here has modified the space around it. And instead of saying that, because these charges feel force, there's field there, I actually go the other way. Because this charge has modified the space around it to fill it with all this electric field, now, when I place a charge here, that charge is going to feel a force. That's given by the amount of charge times the electric field. And because we are drawing it by hand, we don't actually literally fill the whole space, but mathematically it does. So if I place a charge here, even where there's no line going through it, that charge will feel a force going this way. So let's call it 2Q. Then that force will be equal to 2Q times the electric field. Good. Now, I already drew the vectors. Good. So it's a vector quantity. So the electric field points in the direction of what the electric force would be if you place the positive test charge. Good. So this is the divisor field. And with this divisor field, this is how we can answer the question that I posed here. So considering all of this, what do you think? Let me just start off with this. What do you think is the direction of the electric field produced by this long line of charge? Well, so yeah, this is, I'm asking you, so it's a three-dimensional object, right? So I'm trying to illustrate three-dimensional object in a two-dimensional surface. So imagine I have a three-dimensional object here. So if I have point charge placed here, where would it be pushed to? That way. If I have it placed here, push it this way, here, push it that way. What if I move this charge slightly downward? Imagine this is still infinitely long. Will it still get pushed directly to the side? Yeah. So you have to imagine that sort of radially outgoing lines of field. So that if I turn it around and have it face you, what would those lines look like? Radially outgoing from this, what looks like a single point, right? Yeah, so that's the three-dimensional image I want you to visualize. But I have only a two-dimensional board, so I'm only going to be able to draw two-dimensional representation of electric field. So these are the representation of electric field produced by this infinite line of charge. Let me ask you this question. Can anyone tell me what this magnitude of the electric field is as a function of distance? You know how much the force is on a small charge q? So, yeah. Well, 1 over d is the distance dependence. So I can get rid of q. Why can I get rid of q? Not quite. It's much simpler than that. It comes down to this relationship. So force is the charge times the field. Or if you must state it this way, all right, if you want to find the field from force, then the field is the force divided by the test charge. So here, the test charge, this would be the test charge after the fact. Now I'm demoting it to test charge. Before it was equal partner in interaction. So this is the test charge. Well, that's the Q there. Divide it out, that will give you the field. So the expression for the field will be that force divided by the test charge. So the magnitude should be 2k lambda over d. So the distance relationship is, 1 over d, instead of 1 over d squared, which is an interesting result. But now that we have the idea of the magnitude of the electric field, now we can answer my other question. What would be the force between two infinite lines of charge per some length of the charge? So on this side, imagine having that infinite line of another charge of, I don't know, charge density lambda over lambda sub 2 at some distance d sub 2. And let's say you wanted to know the amount of force over some length L. How would you calculate it? Let me put it this way. Let's just look at small section of this that contains charge dq. And I want to figure out what is the small amount of force, df, on this small segment. I take the, not integral. So the whole point of this was that I wanted to avoid the integrals. Because this is one of the power of the tool of the electric field. In deriving this electric field, this represents all that work of integral already done for you. Because to get this answer, yeah, I had to do the integral. But to get this answer, I only had to take this and divide out the charge. But this already contains all that information from the integral, so that you don't have to do it again. This is like software packages if you're a programmer. Or it's like, I don't know, if you're a mechanic, it's like buying a pre-built engine instead of having to build one for yourself. So that's one of the reasons we introduced this intermediary. So that that hard work of doing the integral, you only need to do it once. And once you've done it, and you have this result, you can just use it over and over again. So how do you find this small contribution to this small segment of the charge? What was the relationship between force and electric field? Sorry, yeah, E dq. So force is field times the charge. So the field at this point is still the field due to this whole line of rod. So this will be the amount of electric field as produced by this line of rod times, well, small amount of charge, dq. Yeah? So, well, to find the entire force, I really need to integrate over the whole thing. So let's say you're integrating this over the length L. Length L. Is E, the magnitude of E, constant as you integrate it? Yeah. The question is, electric field at these various locations. They're actually all the same because they're at all distance d2 from the other line. So that's the difference between a point and a line and a line and a line. The line and a line are at the same distance if they're parallel. So E is actually constant, meaning you can pull it outside the integral. So you can say this is electric field times integral of dq over the length. What is this? Like, do you guys know conceptually what this quantity should be? Integral of dq over the whole length? Lambda 2 times something. Not q. Or describe to me conceptually. So if you had to tell me one quantity that's equal to the dq integrated over the length of the rod, what is that one quantity? Yeah, total charge on it, right? So the total charge on it will be lambda 2 times the total length. So this force can be easily calculated as just the electric field. I'll look it up here. 2k lambda over d2, that's the new distance, times the amount of charge in the segment. So lambda 2 times L. So it's going to take a while to get used to using this tool of the electric field, and that's like 2/3 of your exam too. So, but I want you to get used to the idea just how powerful how useful of a tool this is, and that we're going to be using it a lot. Yeah. So, and whenever you feel like you don't have any intuition for electric field, you need some guiding post, come back to this. This is the defining equation for electric field. So you can relate the electric field directly to the force that would be exerted by the field. What I want to do is I want to give you some intuition for electric fields. So, you guys come in with a varying level of intuitive feel for electric field. Some of you have finally understood the importance of this relationship. I'll just tell you that the difficulty you guys are facing, it's common. Each semester, I tell people that this is how electric field is defined. And then when I ask people about electric field, I get blank stares every single semester. And I think, maybe I'm wrong about this, but my guess is that because this is such a simple looking expression, that people underestimate how important it is. That you see it and you just forget about it. Oh, that looks so simple. I'm gonna remember it, and you don't. So I just want to emphasize that this is your connection between what you know, forces, and what you don't know, electric field. So whenever you feel confused about the electric field, this is where you come back to. Not the set of rules that you will hear now. I mean, it's good to know the rules, but that's not the main emphasis. So let me go to fat.colorado.edu. You guys have seen me use this several times. Well, have you seen me use this? Well, this is one of my favorite websites for simulations. It's all free. I think they had a grant or something to develop all this. And one of the simulations that's useful for illustrating electric field is simulation called charges and field. So let me use this to try to illustrate and start to develop some intuition for electric field. So I'm just going to run it. I think it has a project presentation mode where I can use a higher contrast colors. So let me try to do that. Options, yeah, projector mode. All right, that's higher contrast. Okay, so this is a simulation that where if I place a charge somewhere in the space, it will illustrate electric fields that are being produced by this charge. So I keep saying electric field is a property of space. That's what the simulation is illustrating. As in, if I take this point in space here, this point here, I can always ask, what is the electric field? So for example, let me remove this charge. What is the electric field at this point? Okay, let's ask this question. So when you are trying to figure out what the electric field is, the proper question to ask, as I think Kevin was trying to do, what would the force on the charge be if I place the charge here? Right? What would the force on the charge be? It's a simple answer, right? Zero, right? Do you guys believe that if I place a charge here, it would feel zero force? Okay, which means, according to this definition here, electric field must be zero. Yeah, that's what I mean. It's a property of space. Electric field, it's not tied down to a charge. Charges do produce it, but electric field it's a property of that point in space. Now, when I finally actually place a charge, then that point in space now begins to have a non-zero, non-trivial, interesting electric field. But even when this says zero electric field, that's still the property of space. It's like, I don't know. Yeah, I know I always try to do analogies and I'm not good at it. So let me just move on. So, this is something that can illustrate electric field directions. And do these directions kind of make intuitive sense? That's what you would have guessed. And if I put in a negative charge instead, then do these directions kind of make intuitive sense? Yeah?
Sorry, is the forces always going to correlate such things? So as negative is always going to be pointing towards a negative charge, and then positive is always be radiating outwards?
Yeah, so the thing to remember about connecting the force to electric field is that that connection is easier. It's more one-to-one. If you assume that this is a positive charge, assume that this Q in this expression is positive. I mean, it's not always going to be, but if you are trying to figure out the direction of electric field from the force, then you should assume it's positive. Otherwise, you're introducing unnecessary negative signs. So that's what these arrows pointing towards the negative charges indicating. What it's saying is that if I were to place a positive charge here, it would be attracted towards the negative charge. Like, you believe that, right? Yeah. So that's what this field, electric fields pointing toward this charge is illustrating. Okay? Now, these are not actually, what you are seeing on the screen, they are not field lines. They are, I guess they are similar to the vector field representation, right? Where you essentially define a lattice, and at each of these lattice points, you give the direction and you give the magnitude. Here it's done by the opaqueness of the thing. So let me draw what the electric field lines would look like based on this, I don't know, vector field representation of electric fields given by the program. I guess the point comes down to when you're programming, it's much easier to show something like this than drawing electric field lines. When you're drawing it by hand, it's easier to draw electric field lines. Can you imagine drawing every one of these little arrows? Like, anyone want to do that as a homework? No, right? So you know, drawing this vector field, it's a much more cumbersome task for us humans. When you're programming, it's actually easier. Because when you're drawing electric field lines, it has to be one continuous line. So this is how you would draw an electric field line based on this vector fields I see. Let me, just so that I'm not dealing with any singularities, let's say I'm dealing with a positive charge here. And I'm just going to pick a point to start. Here, this point here. And I ask myself, all right, where do I need to go next? I look at the direction of the arrow, and I say, all right, I'm going to have to go left. So I keep going left until I reach my next guiding point. Well, OK, where should I go next? Keep going left. So you imagine connecting these lines, and that's what becomes one of your electric field lines. And you can imagine doing that at several different points. Let me do just 3 more of those. Starting at this point, I'm going to keep following this arrow to have one more field line here. Starting at this point. It's a little bit to the left, but I think it's going to be easier if I just follow down. So I'll do that. So same thing here. It's slightly to the left, but something close to maybe like this. Okay? I'm going to introduce a couple additional rules or conventions that we follow that will make electric field lines represent more quantitative information. The very first of those rules is, I hope this makes intuitive sense so that you don't have to write it down, or like it makes sense and you would remember. So what I'm going to say is, when I first drew this line, I just picked a point to start, right? Like the way I did it, nothing stopped me from picking this point to start and say, all right, it's going that way, that way, that way. Nothing stopped me from drawing this field line, right? So what I'm going to say is, I guess I should write down the rules. So field line rules. So the first rule, number 1, is fields start or stop only on charges. So what that means is that this line that I started from this point, I should really draw backward until it looks like it's starting from a charge. Same thing with these 3 lines. I have to connect them back until they look like they're starting from the positive charge here. So in other words, field line, they can only start on a positive charge. Where do you think field lines can stop? Another positive charge or another what? Yeah, why couldn't field lines stop at positive charge? Yeah, because field line is supposed to go away from positive charge. So you can actually see it here. Let me place another positive charge at the location where that one field line is about to end. So let me place this positive charge here. And let's see what happens to the electric field. So if you're following this, oh wait, it's hard to see. Okay, let me put it somewhere, close enough. You have to draw it very carefully. If you start here, what you will find is that all the field lines are they bend they bend like this and bend go upward. So, there's field line beginning from here, but not one that ends there. All right, let me get rid of it. So the field lines can only start on positive charge, and they can only stop or end on the negative charge. Does this make intuitive sense? Yes? Okay. So that's one rule. I hope that one is intuitive. And the second rule is, this is really why I'm not doing this. I'm not, picking all these points. So, if this was the only rule in place, I could do this. I could pick these three points that are interesting to me, draw field lines starting from them. Drawing these lines. And to make this good, what I can do is, all right, having drawn all these, I'm going to just connect them backward to have them connect back at the charge. Like, what's wrong with that? According to rule number 1, nothing wrong with it. But I would never draw field lines this way because of the second rule. So the second rule, you can state it in two different ways. You could say number of lines starting from charge is proportional to the magnitude of charge. As in, this one plus charge, let's say I drew 4 lines to it. Then the convention that I'm going to follow is that if I have 2 charges, double the number of charges, so stronger electric field, then I'm going to associate double the number of field lines with that. So I will draw double the number of field lines for double the number of charges. And this is closely tied to, there's a reason why we follow this rule. Here's the second version of stating this rule. This is the reason it's important in terms of building your conceptual picture. The number of, I have to call this density of field lines is proportional to electric field strength. Does this make intuitive sense? That where these field lines are closer together, so in this picture, that would be near the charge. So where they are closer together, that represents electric field being stronger. And out here, where they are farther apart, that represents electric field being weaker. Like, that makes intuitive sense? Yeah. So, all these rules, they kind of make sense. That's why I said, I'm writing it down, but you don't have to write it down because it's like, yeah, that's what you would have assumed if I didn't tell you that. And by the way, these rules are what's preventing me from drawing these extra lines here. So why couldn't I draw these extra lines on one side of the charge? Like, what's wrong with that? Well, so I'm going to say, all right, for 2 charges, I associate 10 lines instead of 8.
Because it's not evenly dispersed.
Yeah, it has to be evenly dispersed. You have this intuitive feel that when you have point charge or spherical charge like this, the electric field at this point is not any, or electric field at this point is not any stronger than electric field at some other point that's at same distance. So, but what this wrong drawing is trying to show is that they might be, which is not. That's why these lines are not allowed. Because if you drew them, you are implying that somehow the electric field on this side is stronger than electric field here, and that's not the case. Yeah. So let's see. I think that's it. That's all the rules there are there. These are really the 2 hard rules, that they only start and stop at charges. Now, they are allowed to go out to infinity, never ending. That's fine. And that density of field lines indicate the electric field strength. And this is enforced by following this rule, that as you are drawing field lines, you keep to some consistent number of lines that you are starting from a charge. Yep. Okay, let's look at more fun example. So this is, I mean, if I asked you to draw field lines, everyone would have drawn this. There's no great mystery here. I'm just using this to illustrate the convention that we'll be following. Let's make it more interesting. I'm going to have not just the positive charges, but positive and negative charges. So positive charge here and negative charge here. What do you think it'll look like? Sungmin, what do you think how do you think this picture will change if I put a negative charge here? I haven't dropped it yet, but once I drop it, what do you think it'll look like?
All the lines will direct towards the negative charge.
Okay, so some of the lines will definitely direct towards the negative charge. Let me drop it and see if that's a picture that you recognize as seeing before. Let me drop it here. Do you guys remember anything that looks kind of like this? These, arrows. Where have you seen something that looks like that?
To me, it's magnetic waves.
Not wave. You guys use the word wave way too often. Magnetic field. Yeah, you've seen it with the bar magnet. If you do any demos with iron filings and the bar magnet underneath, then these are sort of the lines that you see. Now, these have nothing to do with the magnet. So this particular arrangement is an arrangement called, let me write it here. This is an arrangement called electric dipole. And if you're a language nerd, then dipole says 2 poles. This is one pole, positive pole. This is the other pole, negative pole, where you're using the word pole instead of charge. So let me just sketch the electric field line here, and we'll go into break after that. Let me use blue. So you follow these rules. So I'm going to say each of these charges are going to have 4 lines associated with it. So one line starting here, one line here, one line here. And I can safely say that near the charges, they're going to look like they're affected only by the charge that they're near to. So these lines look like they're going out here. And these lines look like they are going into this negative charge. Now, as you go farther away, the net electric field will be proportionally more affected by the other charge. So for that, you sort of look at your surroundings. So for this field line, there's no trouble it going straight to the negative charge. So that's it, you're done. For this field line, for some reason, this has no problem going straight away from the positive charge. So I'll just draw it that way. I assume it'll be getting weaker because of the contribution from the negative charge, but apparently that's not changing the direction. Same thing for this line here. The interesting thing happens with these lines. So as you go up, it looks like I'm going to have to bend this way to make my way there. So this line will have to bend something like this to connect to this and actually start and end on negative charge. I guess this did that too, but that wasn't too interesting. This will have to start and end on negative charge. So yeah, so with this picture, where would you say that the electric field is the strongest? Okay, sorry. Let me refine my question, because you could just say electric field is the strongest near either of the 2 charges. That would be the correct answer. So let me put a moratorium or no-go region around the charges. So outside of these boxes that I have drawn, where do you think the electric field is the strongest? Yeah, in the middle where it's straight. And you can kind of begin to see that around this region is where the density of lines will be greater. To see it better, you have to draw more lines. If you drew 8 lines per charge, then this is what it would look like. If you drew 8 lines, here's 4 more lines coming from the positive charge. 4 more lines. And so 2 of those are 2 of the 4 here. So let me draw 2 more here. So if I drew 8 lines per charge, then this is sort of what it would look like. Let me cover this briefly, not too long, so that you can see what that looks like. So with the positive and negative charge here. That's what it looks like. And in this region is where the lines are the most densely packed. And here's where they are not so densely packed, so the electric field is weaker here. Good. So that's the dipole, and it's an example of using the dipole to sort of how you use electric field lines. This is going to be an important tool as we try to apply them to use them to solve. Use them in application of Gauss's law. I'm trying to say it in the right way.